is at once a talk in the South. So this is at once a talk in the South American weekly seminar in geometry, and the last talk of the week of the special geometries and gauge theory workshop based in France. So coordinated by Andres Moreno and Eric Lubo, and also Carl Zippler. So this has been a great week for us who have been attending the seminar, and also our weekly meeting point for the South American geometry community. So during the first minutes of the talk, Igor is going to paste here in the chat the instructions to join our mailing list. So if you want to be informed about future seminars, there's a WhatsApp option, and there's a mailing list option which you can subscribe to. And so please keep an eye on the chat for that info. Also, I would like to thank everyone who participated in the special geometries and gauge theory workshop. This has been a great week with great talks, and I believe we can all agree the speakers have inspired us with a number of collaboration possibilities, and that's been great. So let me now introduce our speaker. This is Umberto Hryniewicz from Aachen University in Germany. And I should also say, on a personal note, I've known Umberto for 21 years, since my first year in college. So technically, he's my oldest mathematical friend. So it's my absolute pleasure to introduce him to both of these events at once. And Umberto is going to tell us about, maybe, Umberto, now you can go to the screen where your full title is available to me. Pseudo-holomorphic curves and applications to geodesics. Please go ahead.
Thank you. Can you hear me?
Yes.
Can you hear? Okay. All right. So first of all, I'd like to thank Enrique and the other organizers for the invitation, the privilege to participate in both events together. I've been following the weekly seminar, and it's been actually very interesting. And today I'm going to talk about some applications of pseudo-holomorphic curves to geodesic flows. I should say that all this is joint work with mostly Pedro Salomão and occasionally other collaborators as well, John Licata, Ana Florio, and Richard Sifrin. Okay, right, so my main goal is to study the interaction between topology and dynamical systems by using methods from analysis, in particular pseudo-holomorphic curves. So I would like to start sharing with you a phenomenon which I think is very interesting. Just to be 100% sure, you're hearing me, right?
Yes.
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 Yes, we are.
Thank you. All right. So let S be some surface. And now I consider the set of oriented, immersed loops without positive self-tangencies. So let me call this lambda J plus. So J plus here is related to Arnold's theory of plane curves. And so let me divide this set by the following equivalence relation. C1 and C2 in lambda j plus are equivalent if and only if there exists a C1 homotopy from C1 to C2 via loops in lambda j plus. Okay, so a typical element here is called a flat knot of j plus type. So let me draw some pictures. So this is a typical curve in j plus. So let me draw a curve which is not in j plus. Okay, so here there is a positive tangency. So not in lambda j plus. Okay, and so in S2, let me draw an example in S2 where curves are equivalent and sometimes and an example where they're not equivalent. So here, if we see the plane of the string as S2 minus a point, this guy is not equal to this guy. Sorry, my mistake. Let me try it again. So this guy is not equal to this guy, but in S2, this would be equal to this guy. Okay, say in S2. Because, in S2, you could take this part of the loop, go around the point at infinity, and come back on this side. Okay. So an element in this equivalence, in the set of equivalence classes, is called a flat knot of j plus type. And in the case of the two sphere and G a Riemannian metric, which is delta pinched, this means that the minimum of the Gaussian curvature is at least times delta times the maximum of the delta of the Gaussian curvature, where delta is a number strictly bigger than 1/4. Then we can combine Klingenberg's estimate for the injectivity radius plus Toponogov comparison theorem to prove that the following eight-like curve, which, if you take away a point, it looks like this, does not appear as a closed geodesic. Right? So let me prove this. Let's say we divide this loop in two parts. The lengths are denoted by L1 and L2. The total length is L1 plus L2. So each loop has length at least twice times the injectivity radius. And by Klingenberg, this is bigger or equal than 2 times divided by the square root of the maximum of the curvature. Now, the whole closed geodesic is the boundary of a convex polygon. So by Toponogov's comparison theorem, the length is no more than 2 pi divided by the square root of the minimum of the curvature, which is strictly less than 2 pi divided by the square root of 1/4 the maximum with the curvature, which is 2 pi half square root of the maximum with the curvature, which is 4 divided by k max, the square root of k max. So you see that on the other hand, these estimates will tell us that L1 plus L2 is at least equal to 4 pi divided by the square root of k max. So you get a contradiction. Okay, that's how you prove this phenomenon. Such curve cannot be a closed geodesic if the curvature is pinched. And the question is, two questions. Does this phenomenon survive for Finsler metrics? And can we rule out more closed geodesics? So the problem is, the problem with trying to answer the first question is that there is no effective Toponogov's comparison theorem for Finsler metrics. In the reversible case, there is something. In the non-reversible case, there are some statements which, in general, deal with much more than just the flag curvatures. So it's not very suitable for applying here. And then the first theorem, which is joint with Pedro Solomon, is stating that if you have a Finsler metric, and it's delta pinched, and delta is a number strictly bigger than r divided by r plus 1 squared, where r is the reversibility parameter. So for geodesic flows, r would be equal to 1, so the number you see here is exactly 1/4. Then no closed geodesic realizes the flat knot of J plus type of the figure 8.
Umberto, can you explain why it is called J plus type?
Well, because in the theory of, right, so Arnold introduced his so-called, to some extent celebrated theory of plane curves. It's an attempt to study the combinatorics of planar curves. Right, so what do we know about planar curves? So if you take immersed curves, then if you fix the winding number, well, we know with a fixed winding number of the velocity vector, any two immersions to the plane are homotopic to each other. So what Arnold proposed is to study curves which don't have some kind of singularity. He rules out certain singularities like tangencies and triple intersection points, and tangencies and yes, intersection points of order 3 or more. And in the complement of this set, let's call them singular immersed curves, he defines like a wealth of invariants, and he tries to study the complement, to characterize curves in the complement of this discriminant, so-called discriminant hypersurface. And of course, Arnold introduces many invariants, and here I'm just ruling out the positive self-intangencies. That's, the so-called Arnold's J plus invariant is related to the positive self-tangencies of the planar curves. So there's a huge theory behind this. So this means that
thanks for the context.
Not only this 8-like curve is ruled out, but anything that you can do by, for instance, here, the curve is coming like this. This is also ruled out because you created some intersection here by going through a negative tangency. So this is still in the same equivalence class of the 8 curve from above. So this is still ruled out. And then you can see that there are infinitely many moves that you can make, and still, all these curves are not allowed as closed geodesics of sufficiently pinched Finzer matrix. Okay. So how do we prove this theorem? And how do you also, this theorem is actually proven in a much broader context. And we actually use holomorphic curves to substitute Toponogov's comparison theorem. So let me explain this context. So we are studying a 3-manifold with a contact form. Okay, so this means that it's a 1 form. And lambda wedge d lambda is a volume form. I will tell you where does this come from later. In this context, the kernel, so this contact form, this condition implies that lambda never vanishes. In particular, you have a rank 2 distribution given by the kernel of lambda. That's called the contact structure. Okay, and right. A knot in M is transverse if it's always transverse to the contact structure. Associated to a contact form, we have a vector field, so-called Reeb vector field, uniquely characterized by being in the kernel of the lambda. This condition here implies that the kernel of the lambda is one-dimensional everywhere, and then you normalize it to be pairing 1 with lambda. So the most important class of examples are the geodesic flows on surfaces. If you have a Riemannian surface, you can consider the unit tangent bundle, the set of vectors with length 1. Okay, so if I denote by pi projection to the base point, I have a one form on the tangent space, given like this. So here, V is a unit vector, and well, actually here doesn't have to be a unit vector, any vector. Zeta is a tangent vector at that vector. So you have this canonical, so to speak, God-given one form. And for this one form, the following is true. Alpha, if you restrict it to the unit tangent bundle, you get a contact form. And the geodesic vector field is equal to the Reeb vector field. So Reeb flows are geodesic flows. Actually, geodesic flows are Reeb flows. Reeb flows, of course, come in a much broader family. And this discussion here actually is not, this example. So there is a way to define contact forms in higher dimension, not only dimension 3. And this example also works there. We can talk about the geodesic flow on any Riemannian manifold. It's going to be the Reeb flow over the associated contact form on the unit tangent bundle. All right. Okay, so now we consider a transverse knot on our 3-manifold with a contact form. assume it's null homologous. Okay, so let me draw the knot here. Now you take a cipher surface. So sigma cipher surface for the knot. So the knot is here. So what you can do is the following. The contact structure, if you restrict the contact structure to the surface sigma, well, the contact structure is a symplectic, becomes a symplectic vector bundle with d lambda. And so symplectic, orientable vector bundles rank to orientable vector bundles over a surface with boundary are always trivial, so you can trivialize the contact structure along the cipher surface. And then you use a trivialization to push K off from itself. You get some push off of K along a trivialization of the contact structure. And then the self-linking number is an invariant of transverse knots of the transverse knot K with respect to the cipher surface, which is just equal to the intersection number of the push off along with the cipher surface. By the way, if you have two cipher surfaces, the difference of the self-linking numbers is going to be twice the first term class applied to the surface, which is given by one minus the other. Okay, so if the first, I just wanted to write this formula because if the first term class vanishes, then the self-linking number actually doesn't depend on the cipher surface. All right, so that's one invariant I wanted to discuss about the transverse knots. Now, if the transverse knot happens to be a periodic Hebb orbit, so periodic orbit of the Hebb vector field, and let me mention that this condition implies that every trajectory of the vector field is going transversely, is flying transversely to the contact structure. So periodic orbits are transverse knots. So a contractible periodic Hebb orbit gamma with a capping disk D has a Koenig-Zander index which is an integer, which we denote like this, CZ gamma D, which is some kind of measure of how much the flow twists along this orbit. Okay, and then I can, so this can be kind of cryptic. If you've never seen this, of course, you have no idea what I'm talking about. But in the case, so in the example that we have to keep in mind during all this talk, in the case of geodesic flows, actually don't need even the capping disk because, if the surface is orientable, then the contact structure admits a global trivialization. So in this case, the Koenig-Zander index, and now it's defined even if there is no capping disk, even if it's not contractible, it's just the Morse index of the closed geodesic. Given by count of conjugate points along the geodesic. Okay, just to, I'm talking about the contact forms, self-linking number, Koenig-Zander index, but should keep in mind geodesic flow, Morse index. And again, we have a formula here. If you have two capping disks, then the difference is given by, of the Koenig-Zander index is given by twice the first term class of the contact structure applied to D minus D prime. Okay, actually here I think there is no, here there is no 2. Correction, here in the self-linking number there is no 2 times this, it's just the term class. Here there's a 2. All right. So let me make a definition here, which is due to Hofer, Vysotsky, and Zander. Every time I talk about Hofer, Vysotsky, and Zander, I'll write HWZ. The contact form is called dynamically convex if C1 vanishes on pi2, and so in particular, Cohn-Lysander indices of contractible orbits don't depend on capping disk by what's written here. Okay, so then the Cohn-Lysander index is of every contractible orbit has to be at least equal to 3 for all contractible periodic Higgs orbit. That's some pretty crazy definition. I just wanted to mention that you can get a contact form by looking at the following very simple picture. I mean, if you look at R4, right? R4 with the standard symplectic form dq dq, so the cotangent bundle of Rn of R2, and then if you look at star-shaped hypersurface, and then if you restrict lambda 0, which is so-called Liouville primitive, kdq minus pdq. If you restrict this to the hypersurface, so here lambda 0 is a contact form if the hypersurface is star-shaped. Okay, if it's star-shaped. And moreover, if the hypersurface is strictly convex, then lambda 0 is dynamically convex in the sense of the previous definition. So every contractible periodic orbit, in this case, I mean, you can take any, you don't have even to talk about contact forms, you can take any Hamiltonian realized sigma as a regular energy level, and then corresponding periodic orbits will have Cohn-Lysander index at least equal to 3. So that's a rich source of dynamically convex contact flow, Reeb flows. And I should also mention that this class of dynamics here, the ones coming from, so the Reeb flows coming from star-shaped convex energy levels. So this class contains all double lifts of all geodesic flows on S2, right? So the unit tangent bundle of S2 with any metric is a copy of RP3, whose universal covering is of course S3, and here's an S3. So you can realize the double lift of the geodesic flow of any Riemannian metric on S2 as some sigma like this. So this class not only is rich because it provides lots of examples, I mean, contains all geodesic flows in S2, but it's very easy to look at this picture and see dynamic convexity into play. All right, so why am I telling you all of this? Because now I can state a characterization of the three-sphere in terms of dynamics, which is exactly the statement that is going to generalize the phenomenon I have explained at the beginning of the talk. I mean, the consequence of Klingenberg plus Toponogov is going to be contained as a very special case in the following results.
Umberto, can I ask you a question?
Yes, please.
In this thing that you were saying about that is in yellow here, do you need to rectify
here?
No, sorry, it's orange, maybe.
Orange,
It was
okay.
right there.
Okay.
When you have a metric on S2 and you lift it, as you said, to S3, you wouldn't get the standard Liouville form, right? You need to rectify.
No. Yeah, no. I mean, there is a very specific way to implement this lifting, so that you get a multiple of lambda 0 on the round S3. I mean, you get a multiple of lambda 0 in the round S3, say here. And then by projecting, I mean, there is, right, I mean, you'd get like a f lambda 0 in the round S3, and then you can project, then you can realize this f is telling you who sigma is. We can sort of, f is telling us how much you have to stretch each direction to get a sigma, to get precisely this lambda here.
Okay, thank you.
Okay, so the theorem I want to talk about now is the following. So if M3 lambda is dynamically convex, and if there exists gamma unknotted periodic orbit with self-linking number, I mean, of course, unknotted means in particular contractible, self-linking number equals to -1, then M3 with the contact structure induced by the kernel of lambda is actually equal to S3 with so-called standard contact form. So the standard contact form is the contact form you get from this round, from the round picture right here. Thinking the round S3 here. Or if you want, the standard contact structure is TS3 intersected with I times TS3. Seeing S3 sitting inside R4, but identifying R4 with C2, and I here is the standard multiplication by I. Okay? So that's a characterization of the three-sphere. So in principle, you could, right, I mean, this result is an extension of previous results due to Hofer, Wysocki, and Zander. And there is a lemma saying that if C is a closed geodesic on a Riemannian metric on S2, say unit speed, then, so if C is a closed geodesic on S2 for some metric, then the flats knot type, sorry, in the flat knot type, representing the flat knot type, given by the figure 8 curve, then C dot, so now this is a trajectory of the geodesic flow, which is the Hebb flow, as we saw before, on the unit tangent bundle, which is RP3. So this guy here is going to be unknotted, and it's going to have self-linking number -1. Okay, it's precisely the kind of orbit which is showing up here. Now there is another theorem due to Harris and Paternine. Actually, here it could be, doesn't have to be Riemannian, could be Finsler. And so if the curvature, so if the flag curvature, so suppose you have a Finsler metric on S2. If the flag curvatures are delta pinched with delta bigger than R divided by R plus 1 square, where R is the reversibility. In particular, for geodesic flows, this is 1/4. then the geodesic flow is dynamically convex. So let's see what comes out of this discussion. We have a theorem saying that if you have a dynamically convex contact form, and if you see an unknotted periodic Reeb orbit of self-linking number -1, it's S3. Now there is a theorem saying that if you're talking about a manifold which is not S3, which is the unit tangent bond of S2, which is a copy of RP3, and if you have sufficiently pinched curvatures, then it is dynamically convex. And then you have this lemma saying that such a flat knot would be an unknotted self-linking -1 curve. So if you put all this together, the proof of the theorem, I stated before, is just observation that RP3 is not S3. That's the proof, because then, if you put everything together, this closed geodesic would force the manifold to be S3. Okay. So this is proved using holomorphic curves. I'll come back to the methods later. By the way, Henrique, what time did we start and how much time do we have?
I think we started 5 minutes late, so we have 15 minutes.
Okay. All right. Thank you. So I wanted to continue this discussion about knots by looking at the following question. What types of transverse knots can be realized by a Reeb flow as periodic orbits in dimension 3, of course. Then there is a result by Etnayer and Grice from 2000 saying that all transverse knots and links can be simultaneously that's critical here, realized as periodic orbits by a Reeb flow on the standard 3-sphere. So basically there is no obstruction to realizing anything, and even if you want to realize everything that exists in the world at once by one flow. And actually this flow is even analytic. Okay. But as we saw before, if we start imposing geometric restrictions like pinching of the curvatures, some knot types start to disappear, cannot be realized. And investigating this kind of question led us, by us, I mean myself, Pedro, and Richard Siffring. That's in preparation. To prove the following. There exists infinitely many transverse knots that cannot be realized as periodic orbits by a contact form which is dynamically convex in S3. So if you impose this restriction of being dynamically convex, in particular, if you're talking about strictly convex energy levels inside R4, then there are infinitely many transverse knots which cannot appear. In fact, we prove a little bit more. We actually prove that if a periodic orbit is symplectically sliced, then it is unknotted and has self-linking -1. So unknotted in the boundary. So let me tell you what slice is. Slice is the following. So here you have S3 inside R4, and then you have the periodic orbit in the boundary, right? So slice means that there is an embedded disk inside the 4 ball. And symplectically slice means that, this is a symplectic disk. Okay, so actually the theorem is saying that if this disk exists, symplectically embedded disk exists, then you can also find a symplectic disk, symplectic in the sense of d lambda disk inside the boundary. So there are infinitely many. So it's already that's a non-trivial fact from smooth form manifold topology that there are many knots which are sitting in S3, which are sliced. They bound a disk inside the 4 ball, but they're not unknotted. They cannot bound a disk inside S3. Okay, and this is also true in the symplectic category, meaning that there are also examples of sliced knots which actually admit symplectic disks, which are not there are slice knots which can be realized as transverse knots on S3 with a standard contact structure. They admit symplectic disks in the 4 ball, but they're not unknotted self-linking -1. Okay, so in particular, the assumption of dynamical convexity allows us to apply this result for convex energy levels. And so let me draw one example for you. There are infinitely many, but it's the 820 knot on Rolfson's table. So I hope I can draw it. Drawing knots is not very easy. Let's see. So a card goes here, and then, right, it goes here, and then it goes here. Right. So here I go back. Okay. Right. So this goes here. Okay. This knot, this is a smooth knot in S3. It admits a representative as a transverse knot with respect to the contact structure. It admits a symplectic disk, and it's not the unknot. So for instance, knots like this cannot exist as periodic orbits, and you can do, there are many operations available for people studying smooth knot theory, which are very delicate, and you can do sorts of all kinds of crazy tricks with such a knot and create infinitely many other knots. Okay, that's kind of a positive result in the sense that, you want convexity to be a property which brings good things for us, right? Convexity should be good, should be nice. Convexity should tell us that the dynamics, can be quite complicated, but not as terrible as a general Reeb flow on S3, because, well, as you saw before, you can realize anything simultaneously by a Reeb flow on S3. So let me give you final result. with this joint work with Ana Florio. So the result says the following. Okay, so basically it tells the following. If two results. First of all, there exists a neighborhood of the round S3, right? So this means that, I'm talking about the round S3 here, and then I'm talking about any manifold C2 close, any energy level C2 close to the round S3. Let's call this neighborhood, I don't know, let's call it U, such that if sigma is an energy level in U, then the following holds. Then every collection, any finite collection of periodic Hebb orbits is the binding of an open book decomposition whose pages are global surfaces of section for the Hebb flow. So in particular, every finite collection of periodic orbits defines a link, which is a fiber link. So a fiber link is exactly this, is a link which is the binding of an open book decomposition. What does that mean? It means that the complement of the link fibers over the circle, and the fibers are, say, cipher surfaces for the link. Basically, that's what this means. And then you have a huge restriction on the knot types of or even link types of periodic orbits, because there are an incredible amount of links and knots which are not fibered. So that's a huge restriction on the knot types. And the second result is the following. If the Finsler metric, actually, this is a Riemannian result. If the geodesic flow is delta pinched for delta bigger than 1/4, sorry, not 1/4, for delta bigger than some number which is a bit crazy, but it's some explicit number, it's around 0.83, then the double lift of the geodesic flow to S3 has the same property. So let's say this property here, I'm going to highlight it, has the same property, meaning that satisfies property red star. Okay, so every time you lift such a flow to a flow on S3, it has a property that every collection of periodic orbits binds an open book decomposition, particularly defines a fiber knot. And not only that, every page of this open book decomposition is a surface which is transverse to the flow, and there is a well-defined return map. You can study the dynamics by looking at the return map to this surface. In particular, what we really prove here is that the flow is right-handed in the sense of G's, and then there is like standard ergodic, sort of classical ergodic methods to prove that once you have this right-handed assumption, then property, then you have this incredible sort of tameness for the periodic orbits as links and knots. Right, so what does this have to do with holomorphic curves? Well, let me just say here on this page. So the main result here is saying that collections of periodic orbits are bindings of open book decomposition. So open book decomposition is exactly the following. You have the, say, a periodic orbit here, and you have surfaces, which are the pages of the open book decomposition, right? And they look like this. I mean, if you look at the point here, transversely, the surfaces are all coming in like this. I mean, they form cipher surface for the link, for the knot. And where do these surfaces come from? They come from projections to S3 of holomorphic curves. Well, in the case of genus 0, you can do this via holomorphic curve. In cases of where the genus is higher, we have to mix holomorphic curves with ergodic methods. But in the end, I mean, you have a lot of ergodic methods playing a role here, but what's really powering them are the holomorphic curves. Okay. There are more slightly weaker results for broader classes of flows, but I think my time is up. I guess I will stop here. Thank you very much for your attention. I hope you are hearing me.
Okay. Have you got questions for Umberto?
Yeah, I have one question.
Go ahead.
So in the second result, this pinching condition is the one that gives is that the one which gives a monotonicity of the first return map to a single closure geodesic?
Yeah, actually, you know, I made a mistake on this number. This number here is just 1/4 actually.
Oh, okay.
Sorry.
Outrageous.
Yeah, okay. Thank you, Pedro. So this, right, I mean, this is a number which allows to estimate appropriately the return time. And then, I mean, this result is really proved, I mean, the result here is really proved by saying, you know, if the, let me write it here. If you have a disk-like global surface section, and then you have the return map, let's say call is the return time for the return map. I mean, tau is the return time for the global surface section. So if the twisting, let's put it like that, if the twisting, there is some global frame of the context structure for which the twisting is bigger than 2 pi times tau mean, where tau mean is the minimum of the return time, then you have this right-handedness, which is the property we need. And then we can estimate this tau mean and the twist for geodesic flow, all in terms of the curvature.
Okay, thanks.
Any more questions?
I have a question.
Sure.
Yes.
You said that the Conley-Zander index is the same as the Morse index when you in the case of the geodesic flow?
That's right. Yeah.
Is it exactly the same? So it should be at least 3.
Well, the dynamical convexity condition is only a condition for the contractible ones. So in S2, for instance, when you have 1/4 pinching, this forces the dynamical convexity. I guess that's what you're asking, right?
Well, in S2, all of them are contractible, right?
No. I mean, sorry. The Hebb orbit is contractible. Right. So the contractibility assumption was on the Hebb orbit. Now the Hebb orbit is the velocity vector. So RP3 has a non-trivial fundamental group, which is E2. So for instance, if you take an embedded closed geodesic in S2, the velocity vector is going to be a generator of pi1 in RP3, right? RP3 is the unitary bundle. So for instance, the velocity vector of an embedded closed geodesic is not contractible.
Right.
And it can have collisionary index 1. So the at least equal to 3 doesn't have to hold for it.
Right. So this result is not saying anything about the figure 8 geodesics in S2, the index of the figure 8 geodesics in S2.
It is. The figure 8 geodesic is the velocity vector is contractible. So with 1/4 pinching, every figure 8 geodesic we have say Morse index at least 3.
But they don't exist, right? That's what you showed.
Yeah, they don't exist. If they existed, yes, that's right.
Okay, so if it's not, are you saying that if it's not dynamically convex, then they have to have index at most 2?
If it's not dynamically convex, then there is a closed geodesic in S2, such that when you lift, and it doesn't have to be also simple. You're allowed to take covers.
Oh, no, I'm talking about the figure 8, right? The figure 8, the one that you can exclude. And you say that that one has index at most 2?
Well, so it's possible to prove that. I mean, in general, if you take some figure 8 knot curve, it could have any collisionary index. But you know, if I guess that's what you're asking, right? I mean, there is no restriction.
Right.
I guess one other comment I can make is that if you relax the pinching a little bit, if you make 1/4 minus epsilon, then you can have an explicit example of even a S2 of revolution for which there is a figure 8 and the collisionary index is going to be 1.
Yeah.
So I mean, the 1/4 is sharp.
Right. Okay, thanks.
Okay, are there any more questions? If not, I have a question.
Yes, please.
So Umberto, the way I mean, we come to talk about contact structures from probably very different directions. The way I know, and I'm used to finding sort of to mass producing contact manifolds, is by looking at projective hypersurfaces in some CPN. Right? These guys have naturally contact, in fact, Sasaki structure.
Yeah.
And they're typically not as simple as the Euclidean sphere. So I guess it would make sense to ask, when is a transverse knot, or how many transverse knots can be realized as Reeb orbits on an algebraic contact threefold? Let's call these guys algebraic contact threefolds. Right? So would it make sense to ask the same question, but in the sense that these knots are realized by some polynomial, homogeneous polynomial?
It makes sense. It makes sense. And that's exactly the kind of question I think it's interesting, because in dynamics, people prove a lot of results by saying, you know, genetically something is true, or, you know, there is some property which almost always holds, but it never holds in the example you want to look at. And you're exactly asking a question specific to examples. I mean, particular curves, right? So I think it's it makes sense. I mean,
but I think it's more than that, because if you had this machinery working, then you could probably, what you would be actually doing is mapping knot invariants into this polynomial ring. So maybe there would be some interplay between
Yeah, there could be. I
invariance of
mean,
the knots and some characters are related to these polynomials, or that's what I would expect to find.
yeah, I mean, expected. I cannot say, but definitely one can look at the complexity of the Hebb flow and try to capture the complexity of the curve, of the algebraic curve,
Right.
or the other way around. The complexity of the algebraic curve could be forcing complexity of the geodesic flow, of the Hebb flow.
Yeah, I agree. Are people looking into this, or is it much too hard with the present day technology?
Well, I mean, I don't think, probably nobody looked into this. And probably the reason is that the questions are already so hard in S3, or very simple manifolds. But I think it's definitely something, at least to take a look and see if it makes sense really. But I think it does.
Yeah, the reason I thought of this is precisely because you're looking at bindings of open book decompositions, right?
Mm-hmm.
So if your threefold is the link of a hypersurface singularity, then by the work of Milner, that's exactly the kind of arrangement you get.
Mm-hmm.
But then all of these guys are the type I'm asking, they're algebraic compact threefolds.
Mm-hmm. Mm-hmm.
So maybe some of the language and even hopefully the techniques could be translated into this framework of Milner hypersurface singularities.
Exactly. No, I think it definitely makes sense to look at it. Definitely, because these are very explicit examples coming out of singularities, and
true.
I mean, the complexity of the possible Hebb flows could even be like a measure of complexity of the singularity, or the other way around as well.
Cool.
I mean, all that said, I mean, of course, that's all what I wish could be done, but that's all we have to really look at before saying something like that. But yeah.
Yeah, my point would be to try and relate the sort of Milner invariance of this of these threefolds to maybe the knot invariance that you get on the other side of it. They might be related. So the dimension of the Milner algebra and things like that, if this could be related to the knot invariance, then I'd be very pleased to read such a result.
Yeah, I mean, any even if it's not coming from a famous or fancy invariant, just any measure of any characteristic of the hypersurface, if it is related to the complexity of the Hebb flow somehow, it's a very interesting thing.
That's very cool. Let's discuss this someday.
Okay, sounds good.
All right, so if there are no further questions, let me thank everyone for attending today, and also everyone who attended the seminar and the workshop the whole week. Let's give Umberto a last round of applause, please.